Welcome. We're diving deep today into, well, a household name from antiquity, Archimedes. But most people, I think, really only know him from a few almost legendary snapshots.
Exactly. You know, the naked guy running through the streets yelling, Eureka. That one's famous.
Right after the discovery about the crown and water displacement.
Or maybe the story of his death, killed by a Roman soldier because he wouldn't step away from a diagram he was drawing.
These are great stories,
Yeah.
absolutely. But our mission today is maybe to peel back those layers a bit and figure out why historians consistently call him maybe the greatest mathematical mind of the entire classical world.
And the sources, they really point to this fascinating paradox at the heart of his life, don't they?
They do. Popular history loves him for the inventions, especially those incredible war machines that held off Rome.
Terrifying machines, yeah. But according to Plutarch, Archimedes himself thought mechanics, engineering, he considered it all ignoble and sordid, not really worthy.
It's almost unbelievable. He saw pure mathematics as the only truly valuable pursuit. The inventions, the physics, the things he's famous for.
Just diversions, apparently. Geometry at play, as one source puts it. It's quite a statement about his priorities.
His real passion, his ambition was purely in abstract thought, in speculation.
Yeah.
So maybe set the scene for us. Where and when are we talking about?
Okay, so he's a Sicilian Greek, born around 287 BC in Syracuse. Lived a pretty long life, about 75 years, until he died during the Roman sack of Syracuse in 212 BC.
And crucially, he spent time studying in Alexandria.
Right, which was the intellectual center of the world back then. He was studying with the successors of Euclid. That's where he really honed his mathematical skills.
And it's that combination of theory and maybe a bit of practical showmanship that leads to maybe the biggest boast in history.
You mean the classic line, give me a place to stand on and I will move the earth. Sasmopteris,
Exactly. That quote really captures him, doesn't it?
It really does, because it wasn't just, an abstract thought experiment. He was making a very real point about the power of levers, of compound pulleys, mechanical advantage.
And he actually proved it, didn't he, for King Hiram II of Syracuse, who was supposedly a friend or relative? Tell us about that ship incident.
Right. So Hiram was perhaps understandably a bit skeptical about these claims Archimedes was making about levers. How could a small force move something truly enormous?
So Archimedes put on a demonstration.
He did. He set up this complex system, probably a compound pulley, though some sources hint maybe it was more like a helix or a screw mechanism.
That was just a machine.
He single-handedly, effortlessly pulled this huge three-masted ship, fully loaded with cargo and crew, mind you, out of the harbor and onto the land. A ship that normally took, crowds of men straining to budget.
Wow. That's quite a statement. A physical proof of physics that you just can't argue with.
Yeah.
It must have really cemented his reputation, at least for practical stuff.
Absolutely. But even before that, probably during his time in Egypt, he came up with something else incredibly practical.
The water screw.
The Archimedes screw, yeah. Simple idea, really. A helix, like a screw thread, rotating inside a tube, lifted water very efficiently.
Mainly for irrigation, right? Getting water up from rivers to fields.
Exactly. A vital piece of technology for agriculture. And it was so effective, versions are, believe it or not, still used today. Simple, elegant, effective.
Okay, but the inventions that really lodge in the popular imagination are the war machines. The ones he unleashed when the Romans besieged Syracuse during the Second Punic War, around 213 BC.
Oh, yeah. The accounts from Plutarch and others, they read like something out of science fiction almost. The Romans were apparently terrified.
They called him the geometrical Briareus, didn't they? After the 100-handed giant from mythology.
That's right. Marcellus, the Roman general leading the siege, was just completely baffled by the defenses. Archimedes had built these incredibly advanced catapults.
What was special about them?
Well, they were designed to be effective at both long range and short range. That was a big deal, technically. Most catapults were good at one or the other.
And then there were the more dramatic devices.
Oh, definitely. Things like machines designed to drop massive weights, huge stones, blocks of lead right onto the attacking ships or siege engines. Imagine the impact.
Crushing. And the most famous one, the Iron Hand.
Manus Ferrea, yeah. This was apparently a gigantic crane, almost like a grappling hook or a beak. It would swing out over the wall, grab the prow of a Roman ship,
What's it up?
lift the front of the ship right out of the water, dangling it there, probably terrifying the crew, and then just let go, drop it or smash it against the rocks or the seawall.
The psychological effect must have been immense.
Probably even more than the physical damage. The sources say Roman soldiers got so spooked, that if they just saw a bit of rope or a beam of wood appear over the wall, they'd panic and run.
They just assumed it was another one of Archimedes' devilish contraptions being aimed at them.
Exactly. Sheer terror inspired by geometry. But what's really fascinating is that this same mind, capable of creating these weapons,
Also applied that same mechanical genius to something completely different, like astronomy.
precisely. Cicero, writing much later, mentioned seeing a mechanical sphere, a planetarium, that Archimedes had built.
And this wasn't just some crude model.
No, no, far from it. It was apparently a very complex mechanism. It accurately showed the motions of the sun, the moon, and the 5 planets known at the time.
So accurate it could even predict eclipses.
That's what Cicero claims. It demonstrated the mathematical predictability of the heavens. Livy, another historian, called him unicus spectator caeli saturumque,
Meaning?
the singular observer of the sky and stars. He wasn't just a theorist. He built working models of his understanding of the cosmos.
Okay, so he could design weapons to stop an empire, build models of the universe, but still thought that was all secondary, just messing around.
Pretty much, according to Plutarch anyway. To really get what drove him, what he truly valued, we need to look at the mathematics he inherited.
Right, the context. Where was Greek geometry before Archimedes came along?
Well, it started practical. Think Thales bringing measurement techniques back from Egypt. Basic stuff, like proving angles and shapes.
Then the Pythagoreans came along. The famous theorem, obviously.
Right, but they also hit a major snag. A crisis, really, when they discovered incommensurables.
Incommensurables. Sounds complicated. What did that mean in simple terms?
It means some lengths just can't be expressed as a simple fraction, a ratio of 2 whole numbers compared to another length. Like the diagonal of a square compared to its side, you get the square root of 2.
Which isn't a neat fraction.
Exactly. And for the Pythagoreans, who believed everything in the universe was based on whole numbers and their ratios, this was, it was deeply troubling. It broke their model.
So the beautiful mathematical world had this, fundamental crack in it.
Kind of, yeah. This wasn't really resolved until maybe the 4th century BC with Eudoxus. He developed a more sophisticated theory of proportion.
And crucially, the method of exhaustion.
Yes, the method of exhaustion. That was key. It allowed mathematicians to rigorously calculate areas and volumes of curved shapes like cones, pyramids, spheres, by approximating them with polygons and sort of exhausting the difference.
Okay, so that's the toolkit Archimedes had. This is the foundation he built on. What did he consider his greatest contribution? The thing he was most proud of?
It comes down to the cylinder and the sphere. He actually requested that his tombstone feature a diagram of a sphere perfectly fitting inside a cylinder.
Along with the ratio, right?
Exactly. The ratio of their volumes. The cylinder's volume is to the sphere's volume as 3 is to 2. That simple, elegant relationship, that discovery, he felt, was his most significant achievement.
More important than moving the Earth or defending Syracuse. That's amazing. But the really mind-blowing insight into his genius, that came much, much later, didn't it? With the discovery of that palimpsest manuscript.
The method, yeah.
Yeah.
Finding that was like finding Archimedes' secret notebook, his workshop manual.
Because it wasn't the final polished proof. It was how he found the answers in the first place.
Precisely. It reveals this incredible mechanical method he used for discovery. It was essentially a proto-calculus technique, centuries ahead of its time.
Okay, break that down. What was he actually doing in this method? How did he use mechanics to find, say, the area of a weird shape?
He'd imagine the shape, let's say a segment of a parabola, that curved shape sliced up into an infinite number of incredibly thin parallel strips, like infinitely thin slices of bread.
Okay, got the slices.
Then he'd mentally place these slices on a make-believe lever, a virtual balance beam, and he'd balance them against slices from a shape he already understood, like a triangle or a cone.
So he's weighing shapes against each other in his mind, using the principle of the lever, using physics to guess geometry answers.
Essentially, yes. He used the principles of mechanics, specifically the law of the lever, which he understood better than anyone, to figure out the ratios of areas or volumes. It gave him the answer, the intuition.
But that wasn't enough for the Greeks, was it? That intuitive leap needed rigorous proof.
Absolutely not. That mechanical reasoning was just for discovery, for suggestion. To actually prove it rigorously, to satisfy the demands of Greek mathematics, he then had to go back and use the accepted traditional method of exhaustion.
Which was much harder and more painstaking.
Oh, incredibly so. But he did it. He found the shortcut, the elegant insight using his mechanical analogy, and then he did the hard geometrical slog to prove it formally.
That's just Wow. It's like inventing a calculator, but then insisting on doing all the long division by hand, just to double check. The commitment to rigor is astounding. He basically invented the core idea of integration.
He really did. Look at his work on the quadrature of the parabola. He proved that the area of a parabolic segment is exactly 43 the area of a triangle with the same base and vertex.
And doing that involved summing an infinite geometric series, didn't it?
It did,
Yeah.
geometrically. A stunning piece of work. And then there's his calculation of pi in measurement of a circle, setting the benchmark for
How
centuries.
accurate did he get?
By inscribing and circumscribing polygons around a circle, eventually getting up to 96-sided polygons, which must have been incredibly tedious to calculate.
Especially with Greek numerals, right? Not exactly easy for complex math.
Not at all. But he managed to pin down the value of pi between 701 and 357 Hif, which is roughly between 3.1408 and 3.1429. Phenomenally accurate for the time.
That work on pi, dealing with those calculations, maybe hints at another challenge he tackled.
Yeah.
Dealing with truly enormous numbers.
Yes, which led to the Sandreckoner. You have to remember, the standard Greek number system wasn't built for huge quantities. It kind of topped out conceptually around maybe 100 million.
Not nearly big enough for Archimedes' imagination.
Apparently not. So he invented a whole new system just to handle numbers far larger than anyone had ever needed to consider before.
How did it work?
It was based on powers of a myriad, which is 10,000. He created these orders and periods of numbers, essentially a system using powers of 10812 as a base. It allowed him to name numbers astronomically large.
How large are we talking?
The largest number his system could theoretically express would need. Well, modern estimates say something like 80,000 million digits to write down. Utterly immense.
Okay, but why? Why invent a system to write down a number you could never possibly use in the real world? What was the point?
The point was the demonstration itself. He wanted to show that any finite number, no matter how large, could be mathematically named and reasoned about. And he chose a great example problem, calculating the number of grains of sand needed to fill the entire universe.
The ultimate large number problem.
Exactly. And to make sure his system was up to the task, he used incredibly generous assumptions. He hugely overestimated the size of the Earth, the distances to the stars, the size of the universe as then conceived.
He made the problem harder for himself just to prove his number system could handle it.
Right. And his conclusion, even using these vastly inflated figures for the size of the cosmos.
The number of sand grains required was...
Less than $1063. A huge number, certainly, but comfortably within the range his new system could express. He proved that even the uncountable could be counted, or at least named.
But there's a fascinating aside in the Sandreckoner, isn't there? Something completely unrelated to sand or big numbers, but hugely important for the history of science.
There is. In the introduction, almost casually, Archimedes mentions the work of Aristarchus of Samos.
What did Aristarchus propose?
Archimedes states clearly that Aristarchus had put forward a hypothesis, likely in a book that's now lost, suggesting that the Earth revolves around the sun and that the sun and the fixed stars remain stationary.
So this is direct contemporary evidence of a heliocentric theory centuries before Copernicus.
It absolutely is. From Archimedes himself, it's invaluable proof that these ideas were being seriously discussed in the 3rd century BC. That one treatise gives us both a way to name the infinite and a glimpse of revolutionary astronomy.
Incredible. Okay, let's circle back finally to where we started with that most famous story, the crown, the bathtub, the eureka moment.
Right, which connects to his foundational work in hydrostatics, laid out in his treatise on floating bodies.
The problem, said by King Hiram again, was the goldsmith cheating. Had he mixed cheaper silver into the supposedly pure gold crown?
Yes, and Hiram needed Archimedes to figure it out without damaging the intricate crown, no melting it down.
So Archimedes had to invent, essentially, the science of fluid dynamics and density on the spot.
Pretty much. He started from basic principles, postulates like the idea that a less dense fluid will be pushed out of the way by a denser one. This led him to formulate the principle of buoyancy, why things float.
And the bathtub moment, the eureka. What was the actual realization?
The realization was likely that an object submerged in water displaces a volume of water equal to its own volume, and that by measuring this displaced volume, he could determine the object's density or specific gravity.
Okay, so how did he apply that to the crown? It wasn't just dunking the crown itself, was it?
The most plausible method, the one described later by Vitruvius, involved comparing the crown to equal weights of pure gold and pure silver. Ah, weights, not volumes. Okay.
So you take the crown, you take a lump of pure gold that weighs exactly the same as the crown, And you take a lump of pure silver that also weighs the same.
Then you submerge each one in turn.
Exactly. Pure gold is very dense, so the lump of gold would displace the least amount of water. Pure silver is less dense, so the lump of silver would displace the most water.
And the crown, if it was a mix,
Would displace an amount of water somewhere in between. By measuring precisely how much water each one displaced, he could figure out the exact proportion of silver the cheating goldsmith had mixed in.
Brilliant. It's the birth of quantitative analysis using fluids, all sparked by a suspicious king and maybe, just maybe, an overflowing bathtub. #tag outro. So when you pull it all together, here's a man who, yes, he was a reluctant engineer by his own account, yet his inventions terrified Rome and held them off for years.
A man who laid down the fundamental laws of levers and buoyancy, principles we still rely on every single day. But whose true passion, whose heart, was really set on the pure, abstract beauty of geometry. Finding that perfect ratio between a sphere and a cylinder meant more to him than anything else.
He really did bridge that gap between the purely theoretical and the incredibly practical, even if he sort of downplayed the practical side himself. He was centuries ahead in mathematical thinking, discovering tools that wouldn't be fully developed until Newton and Leibniz. The sheer scope is, well, it's breathtaking.
It really is. And it leaves us with that final, poignant image, doesn't it? Archimedes, completely lost in thought, drawing diagrams in the sand or maybe on a slate with oil.
So absorbed, he barely notices the Roman soldier who's about to kill him, begging for just a moment more to finish his problem.
Which leads to maybe a final thought for you, our listener, to ponder. In our modern world, with all its complexity, its constant distractions, its frantic pace, what fundamental truths, what simple, profound insights like the ones Archimedes chased might we be missing?
What might we discover if we could recapture even a fraction of that deep, undistracted, contemplative focus he seemed to embody right until his very last breath?
A challenging thought indeed. Something to consider. Until our next deep dive.